Good morning, class. Today's video is for, so this is the video for, what is today? Today is October 5th, so this is the video for October 6th. And we're going to go over a few questions on the quiz first, and then start covering semiconductor etching. All right, so the quiz, like I said in my announcement, I was very happy with the results. The average was about 9 out of 10, and that's great. I think that the quiz was a good set of questions to test whether you've learned learned the material in the course. And I welcome feedback on the quiz. So I just want to discuss a few questions. Okay. So question number one, so, you know, an acceptor atom, all right, is negatively charged. And three people got this wrong, and I think that's just a matter of just, you know, kind of understanding things but being backwards thinking and just getting mixed up. But of course, since an acceptor atom accepts an electron, okay, it becomes negatively charged. So the answer to that was A. Number 5, okay, that question 7 people got wrong, and I guess in retrospect that might make some sense here because I said for which of the following can a chemical reaction take place at the substrate. So the depositions with chemical reaction so of course you know, CVD is one because that's basically almost what the title is, chemical vapor deposition. We know evaporation is not, but also sputtering. Because sputtering can include a plasma, and so it can include chemically reactive species that can cause a chemical reaction to the substrate. So the answer was E, B, and C. Number 7 was on strain growth, and you know, so you have silicon, and I used germanium 30% contact, and you were supposed to refer to figure 6.4, which basically shows that you know, there's this range. I mean, here it's the crystal is intact, so this is germanium percentage, and we're here at 30%, and this is thickness. And so there's 2 lines there, and above this it's relaxed, meaning broken, and below that it's intact. So you were supposed to put down 7 to 60 nanometers, which is, you know, from there to there. So the answer was B. And the only other one that was, I mean, there were 2 wrong for problem 10 about optical lithography for liftoff, and you know, and I felt that because it had been covered both in class and also in the clean room videos themselves, that you understand that for liftoff you do not perform a post-development bake, and 2 people got that wrong, so that wasn't that big of a deal. So on an overall basis, very good. And like I said in my announcement, when everything is tallied up in terms of homework and quizzes, you know, I will implement a curve only if it improves grades. I mean, you know, if, you know, for example, 90% is typically, you know, kind of an A minus type range, and so, you know, giving everyone an A minus or above on the quiz, I have no problem with that. I prefer that. So, we can talk tomorrow during the chat session if there's any questions on the quiz to go over further, but I think that the quiz was basically a success. Okay, so now for the material for today. And today's lecture is on semiconductor etching. And I want to sort of, along the lines of, again, the material today is more knowledge-based than calculation-based. There's not going to be any equations today. We're just going to cover material that you're expected to be able to show that you understand in the homeworks and the quizzes. And so maybe I can neatly do this on two sides of the board. So I'm going to put this etchants, which means things which etch semiconductors. And over here, I'm going to put etch masks. Okay, and now, okay, I'm using the word mask there. I could use different words. That's the usual word that's used. You could use etch resists, for example, but that would point to photoresist, and it's not always a photoresist. So, we'll cover this in a second here. So there's sort of two things to understand. That there's different ways, different chemicals / plasmas, basically, that can etch semiconductors. And there's various things you can pattern on the substrate to resist the etch. And so this is going to be a relatively simple discussion. The reality is that performing a semiconductor etch, it involves these two components. Maybe I can get started over here on etch masks. So basically, if this is your semiconductor, okay, this is your etch mask, and we'll describe in a minute, the couple things you can do. But basically, you pattern an etch mask or a stencil, whatever word you want to use, with openings where you want to perform your etch, and then basically the idea is that after your etch, all right, you have, I'll draw it like this. You have removed, etched. Never really thought too much about where the word etched came from, but it refers to removing within some sort of chemistry, and so I've drawn a sort of a profile within with respect to the etch mask here, or the etch stencil, whatever you want to call it, and we'll get back to that in a second. Okay, so those are the two things. And so you can even label them 1 and 2. And now, so semiconductor etches, and there's basically 3 types, kind of. So we'll do A, wet etches. For example, acids. Now, in this lecture, we're not going to give you, a whole list of recipes of different acid combinations or base combinations that will remove certain semiconductors. Um, I'm just going to present to you the knowledge framework. And in a sense, it's a knowledge framework that has to be filled in at some point in your career when you are faced with the problem of having to perform some etch of some semiconductor. One second. Sorry. Okay, I'm back. So, you know, there's a few listed in the textbook. Um, I guess what I will say is that, you know, I'm not going to give you a quiz where I'm going to say what particular recipe etch do you use to remove this semiconductor or something like that. Because, you know, I mean, when it comes right down to it, you're in your career someday, you're going to be faced with having to etch, I don't know, indium arsenide. And then you're going to look it up, basically. And what I want to give you here more is kind of a framework of the different types of etches. Now, let's continue going here. B is called dry etching. Because it doesn't involve anything wet, a liquid, but it's particularly, in fact, I could almost say IE because, you know, it's always a plasma. Plasma. So for here, there's what's called a reactive ion etcher. Or RIE. Which there's a nice figure or a photo of one in the book, and it basically is a chamber where you place your sample in, and then you close it up and you vacuum out the air, and then you introduce a gas, and then you institute a plasma. And in this case, the plasma, you know, I'll extend the parentheses here. Now we all understand what the plasma is. That's an ionized gas. It's generated by radio frequency. You know, it's similar to a microwave in the sense that you have your chamber, you introduce your sample, you pump in gases, whatever species of gas you want to put in, and then you sort of pipe in radio frequency energy. It's different from a microwave in the sense that it's not microwaves. It tends to be more sort of meter waves, 13.6 megahertz, that is used to introduce enough energy to ionize the gases. And then once they're ionized, they can cause chemical reactions at the substrate and cause etching. And then C, there's ion beam etching. Which is kind of what it sounds like, which is where you have an apparatus, a piece of equipment that you place your wafer in, and you're able to generate a beam of ions that impinge on the substrate and actually kind of just mill. This is, you know, essentially milling. Now you'll use this far less in your career. It's a more specialized type of etching, and you know, it kind of is what it sounds like. In the machine, you can sort of raster around and create etched features. And so, in a certain sense, ion beam etching. Well, no, you still really need an etch mask because, you know, the beam is not perfect, but it allows you to make some more mechanical. Now, D, and this is really, in fact, I'll put it. Well, so I'm gonna. I didn't leave myself enough room here. Let me lower this one here, because I like leaving the board with kind of a smooth description of things. So ion beam, and etching. Sort of, you know, milling. Now there's some subcategories of these two that I'll pay special attention to, which is here there's crystallographic. Now here I'm introducing some terminology that describes what happens when you perform the etch. Now here, and I'll sort of I'll make it a little bit more exaggerated here. This is isotropic etching. Meaning the etchant comes down and it sort of attacks in all directions. Isotropic kind of means in all directions. I'll draw another profile here. So if it goes relatively straight down, so this is isotropic etching, this is anisotropic etching. And you know, that's kind of what it sounds like. The etching is more directional. Now this only occurs for dry etching. And finally, there's crystallographic plane etching. So you see here for the isotropic, it's kind of curved because it's going in all directions. Here, for example, particularly, this is a crystal plane. And typically, a typical recipe is, this is the 111 plane for KOH in silicon. Meaning, if I perform so this would be crystal plane etching or crystallographic etching. I'll call it crystal plane etching. Is this one here. So these are the sort of three types of profiles that you can get. Isotropic is more typical with wet etching because the liquid tends to go everywhere, except if you use particularly some. See, what happens here is that the etching, it depends upon crystal plane. So, for example, for potassium hydroxide will not etch the 111 plane in silicon. It just won't do it. And so it removes everything else except stopping on that plane. And then isotropic etching is typically with dry etching, some sort of reactive ion etching. And then here under B, there are more things here, but I'm going to call it the Bosch process. Okay, and in the Bosch process, so 1, 2, 3, 4, and I'll leave a little space here for my 2 etch masks. In the Bosch process, okay, if you have an etch mask, for example, now I'm going to make an etch mask that's a flat thing like that, and if I perform an etching, what will happen is that I will get I will start to get some etching like that, where it goes in a little bit. Oops, I'm doing it the wrong way. All right, let me do a pillar. All right, so basically it will etch like that. Making a pillar. So you do it in one step, and this for example could be with SF6 plasma, and then B, you do a fluorophore, and C4F8, and so this etches and this coats, which is a little difficult to understand how an etching process can produce a coating, but it does. And so basically, A, you etch, and then B, it produces a coating all the way around here. And then what happens in the subsequent step is that the next step tends to remove more vertically, leaving that coating, and so you get kind of a profile like this. Okay, because the subsequent, you go, so A, B, the coating, and then back to A, and then when you do A, it tends to remove the coating vertically faster, and so it doesn't etch inward as much, and so you can sort of keep going vertically like that. And so this is a cyclic process. Where you first introduce one gas and another gas back and forth, and you can go in steps like this, and so you can perform a very, very deep etch, deep straight etch. So Bosch. So this is the sort of the 3 categories with the 2 subcategories in wet etching, crystal plane etching, and in plasma etching, the Bosch or cyclic process. And then these are the 4 resulting profiles that you can get. Isotropic, where it just goes in all directions, anisotropic, where it tends to go more straight down. Crystal plane, where it stops on the plane of the crystal. And then Bosch, where you use a cyclic process that allows you to sort of keep stepping downward and making a very deep, high profile. And those are the 4. This describes the main categories here. All right. So now what I'm going to do here is, I'm going to put my category 2, which is the etch mask. So, what we've described already is how you etch a semiconductor, and this lecture is meant to provide you with a kind of outline or overview. You should refer to the listed sections in the textbook to get more detail here. But you can sort of take a picture of this board, the 3 categories: wet, dry, ion beam, the subcategories of wet, crystal plane etching, and Bosch process. And those are the 4 resulting etch profiles you can get. And now, okay, we've described all this in terms of, all right, we produce some etch mask, some stencil in the material, and so we want to understand, well, what should that be? All right, and so one, it could be photoresist, where I'm using PR so I don't have to write it out, but hopefully by now you understand that I mean photoresist when I say that. Now photoresist is good for certain wet etches, not all. Now, getting back to the quiz, for liftoff you don't do a hard bake, but when you use it for an etch mask, you do use a hard bake to make it sort of stronger and more resistant to the etch. For certain wet and there's 2 basically that you can use. I usually use CF4 or SF6. Now what do I mean there? Okay. The main gases for reactive on an etching are CF4 and SF6, which etch silicon nitride, silicon dioxide, and silicon. So photoresist can be used as an etch mask for using CF4 or SF6 to etch, for example, silicon nitride. Okay, so photoresist can be used as an etch mask, a stencil. So it's the most convenient thing to use, right? Because photoresist, you spin it on, you expose it as you've seen, you make an opening, boom, you're done. And so that's your etch mask. Okay, and it works for certain wet etches and for plasma etches using, for example, CF4 or SF6 to etch silicon nitride. And now, the next most used etch mask is silicon nitride. Okay, and for for plasma etching, for example, gallium arsenide, or most 3,5 semiconductors. For most 3,5 semiconductors, use a plasma. The plasmas are usually chlorine-based, and those plasmas will attack photoresist, and so photoresist can't be used as an etch mask. But silicon nitride will stand up to them, and so you use silicon nitride as a resist match, as a etch resist stencil when you need to do sort of more aggressive etching. And roughly it goes in that direction, which is that silicon nitride can, well, of course you can't use silicon nitride as an etch mask for things that etch, things like silicon nitride. So you wouldn't use that for the same, like you wouldn't use a silicon nitride etch mask for silicon dioxide, for example. But it kind of goes in this direction, and you sort of see you're starting to see the starting of having recipes and things like that, because particularly if you need to perform etch some features in like gallium arsenide, you would first deposit silicon nitride, you would spin photoresist, you would make the openings, you would use that as an etch mask to define the silicon nitride, and then you would strip your photoresist and you would use the silicon nitride as a subsequent etch mask for a plasma, a chlorine-based plasma. I'll put that in parentheses, like gallium arsenide. Okay, so that's what I wanted to cover today. This board, if you followed it, and you can read my handwriting here, is a nice synopsis of what I want you to understand about etching. That there's sort of two things that you have to understand: what etchant you use, and what etch mask or stencil on the semiconductor wafer you have to use. There's wet, dry, or plasma, and ion beam. Within wet, there's a subcategory of crystal plane etching. Otherwise, it tends to be isotropic. Within dry etching, there's a subcategory of Bosch process or cyclic process that gives you a very deep, straight profile. And there's some nice, pretty pictures in the book. Over here are the 4 profiles. This board's a little bit messed up because I use this for my profiles, which can be isotropic, meaning going all directions, anisotropic, meaning mainly straight down. Crystal plane etching, where it stops on the plane, and typically that's using KOH to etch silicon, stopping on the 111 plane. I guess I can just add maybe a slight thing here, since you do have a homework problem on it. That for crystal plane etching, I guess I'm not making it very big here, but you can probably see something. Okay, if that's my crystallographic box, my crystal box, all right, if this is the 100 plane, then the 111 is defined by that triangle there. Okay. So if you had a 100 surface like here, it would etch, and you had an opening over here, it would etch down to that triangle. And then for etch mask, I mean, there are other things you can use, but the main 2 categories are simply using photoresist itself, which can work in a lot of cases, but not always. In cases where photoresist doesn't work, you tend to use silicon nitride, and so then, you know, nicely, you know, it sort of works out because photoresist can be used as an etch mask for silicon nitride using a plasma etch. And so you can use that to put down silicon nitride, make a photoresist stencil, make openings, etch your silicon nitride, making openings in it, and then use that, remove the photoresist and use that as your stencil for a subsequent etch. All right, that's it for today, and we'll get together tomorrow morning for the class.